YouTube? So today I'll present a pretty simple proof. I believe it's the Euclid proof for the fact that there are infinitely many prime numbers or prime integers. So what we want to prove, okay, let me find a better marker. Okay. We want to prove that there are infinitely many prime integers. So this uses a lot of number theory. So I guess it's going to be a number theory video. And this builds up upon previous concepts, which I don't think I've covered in previous videos, but I'll use here, and I'm sure it'll be pretty understandable for most of you people. So if there are, so for the sake of contradiction, so for the sake of contradiction, which is what FT's SOC means, suppose that there are only finite amount of prime integers. So there are finitely many, I'll just call prime integers pi. Okay, so then that means that you can denote the prime integers as the following. You could say p1, p2, p3, all the way to pk, such that k is part of the natural numbers. Let me get an eraser. So you have that. So suppose you have a number, say p1 times p2 times p3 all the way to pk. So the product of all the prime numbers. Then you add 1 to the n and set that equal to n. So there's a theorem that was proved. I forgot who it was that proved it, but the theorem basically stated that any integer has a prime factor. Okay, so what does that mean? Well, that means that n equals p1 times p2 all the way to pk plus 1. This number, this whole number, has to have a prime factor. But since there are only finitely many prime integers, that prime factor, which I'll just call, I don't know, a, so I'll call a the prime factor in question. A has to be one of these. So A has to be one of the P1 to PK. So let's just say that A is equal to, I don't know, P, like I'll just call it Z, PZ. So it's one of these terms. So what we know about this, first of all, that means that PZ divides N. Or in other words, N is divisible by one of these in here. What that also means is that this entire string or sequence, obviously P1, P2, all the way to PZ, that product, or sorry, PK, not PZ, that product, that entire product is also divisible by PZ, because remember, PZ is one of the members of this infinite, or not infinite, this sequence of prime numbers and their product. So, oh, I forgot to mention what this dividing symbol means. So, if you have two integers, a and b, you have like a dash or a slash b. So essentially what that means is that for all integers a to b of the, I guess, integers, then there exists an integer, another integer, n, z, such that an equals b. So essentially, you can take the integer a, multiply another integer to n, and that'll equal b. And because of that, you could say that a divides b, or in other words, b divided by a is equal to a whole number n. But we haven't gone to division, but I just wanted to make it simpler for you guys to understand. Okay, so we have that in order. So what about this extra term 1? Well, there are other things that need to be proved, but I guess I don't really have the time because this room will be taken up by a class I'm in later on. But I'll just try to conclude this as quick as possible. So essentially, if P of Z divides n, then that means P of Z also divides P1 plus P2, or sorry, P1 times P2 times all the way to P of K, and then plus 1. So there's a certain sort of lemma that I guess I could show. That's if A divided by B plus C is true, and A divides, if A divides B is also true, then A divides C must also be true. So I could prove this in a later video, but the proof is pretty trivial and easy to understand, so I won't cover it. Okay, so back to this. So essentially, we could set B equal to this infinite product. So P1, P2, all the way to Pk. Okay, then you could set C equal to 1. So in other words, we know A is Pz. So this would mean that A divides C would be true. So that would mean that prime P of Z divides 1. And as we already know, this cannot be true, and I'll just justify that. So first of all, we know that the least prime number is 2. So at the very least, P of Z has to be equal to or greater than 2. So obviously 2 doesn't divide 1 because there's no such integer that can multiply by 2 such that it equals 1. That can't happen because n would have to be 1/2, and that does not exist in the integers. So one thing that we also know is that in the natural numbers, any number that's not 1 has to be greater than 1. So basically essentially any prime number doesn't divide 1. And that brings us to a contradiction. I don't know if that explanation was good, but this is a contradiction. And therefore, the claim that we made at the very beginning, which was that suppose there are finitely many prime integers. Well, I guess you can't suppose that there are finitely many prime integers, and what is the exact opposite of that statement? Well, it is that there are infinitely many PIs, or prime integers. And then I guess QED. Okay, thank you for watching this video, and I'll see you in the next video.